போடுங்க. I all welcome for the lecture series on analytical machines 1. In the previous classes, we had discussed about the introduction about analytical machines, and we also discussed about what is magnetic circuit and different laws which governs the analytical machines. We discuss about Faraday's law of electromagnetic induction, and we discuss about different parameters which is associated with the magnetic circuit. And today we are going to discuss about the transformers, right? I clearly told in analytical machines 1, it is classified into 5 components. The unit 1 is about introduction to magnetic circuits and introduction to machines, and unit 2 is purely dedicated for transformers, and later on we are going to discuss about DC motors, DC generators, okay, and also we have the speed control of the DC motors, okay. So before going to the transformers, it is a very important component in analytical power systems. Without transformers, we cannot do anything in power systems, right? What is a transformer? What is the usage of the transformer, or why it is or where it is used in power system? Okay, transformer is a device. Actually, it is a static device. Transformer is a static device used for transferring the energy from the one side of the circuit to the another side of the circuit without any electrical interconnections. Because it is transformer is electrically isolated, but it is magnetically coupled. That's why it is called as a transformer. Transform energy from one side of the circuit to the another circuit without any electrical connection. Only actually it is acting in a electrical isolation. Okay, so what is the other need for the transformers? Normally, when you're going for the power systems, we are generating the power at the generating station at some 11.2 kV. Okay, and the power generated from the generating station, it has to be transmitted to the distribution stations through the long transmission lines, right? So when you want to go for transmitting the power for a long distance, we supposed to have the transformers, because if you are transmitting the power at 11.2 kV through the long transmission line to the distribution station where we connect all the loads, right, where we connect all the loads, then it is going to be a big problem, because the losses is going to be very huge if you are transmitting the power for the long distance at very low voltage levels. Okay, so for this situation I need a transformer. What a transformer can do, if I put a transformer here, this transformer can step up the voltage from 11.2 kV to 400 kV or to 30 kV or 760 kV, right? So these level of voltages, we call it as a transmission level voltages, starting from 230, 400, 760 kV. Okay, so whenever we step up the voltage from 11.2 kV to higher voltage levels, the transmission losses will be reduced, right? Why it is reduced? We know that whenever we are going for a transformer, right? So transformer is a static device, I told. So inside the transformer, we have two windings. One winding we call it as a primary winding. The other winding we call it as a secondary winding. So when you are applying the voltage at the one end, I call it as this is a primary winding. This is my secondary winding. Okay, this voltage will be V1. So this current will be I1. and this will induce an voltage in the secondary side, and this voltage we call it as a V2, and this current this call is I2. Normally in case of a transformer, the input power V1 I1, which is equal to V2 into I2. It means whenever you step up the voltage, definitely the levels of current is going to decrease. Okay, so that is the principle we are using in a transformer. It is very useful for transmitting the power in long transmission lines, right? Because when you are step up the voltage from 11.2 to this level of voltages 230, 400 and 760, definitely the current I2 levels is going to be decrease a lot. That results in your I2 square R2 losses, that we call it as a copper losses in case of a long transmission line. It is also decreases. Again, when you're coming for a distribution, I cannot distribute the power at a very high voltage. In that case, again I need another transformer, but this transformer is not a step up transformer, it is a step down transformer. So I will represent my transformer as T. Okay, this transformer will step down the voltage from your 760, 230 and 400 kV. These are the transmission level voltages. This voltages are converted into the distribution level voltages, right? It starts from 110 kV, that might be a 66 kV, or it might be a 33 kV, or it might be a 11 kV, or it might be 6.6 kV, or it might be your 440 volt 3-phase supply, then 230 volt single phase supply. Okay, so we need to step down the voltage from transmission level voltages to the distribution level voltages. For that also we need a transformer. So transformer is an integral part of a power system. Without transformer, we cannot do any function, right, in power system. That's why it is very much needed to study about the transformers. Okay. Actually, this class, this lecture class, we want to discuss about the basic operation of the transformer. If possible, we'll trying to draw the phasor diagram of a transformer under various loaded conditions. Okay. Now we'll go to the what is the basic operating principle of a transformer. Okay. So I clearly draw a sketch about the transformer, right? You know that what is a transformer. I'll read out that transformer again. Normally your transformer will look like this. So this is called as a magnetic core. Okay, this is magnetic core. Normally this core is not made up of a complete solid piece. It is a laminated core. It means this iron core is sliced into thin laminations, and all these thin laminations are compressed together to form a solid core. Okay, what is the need for laminating the core and compressed together? Because whenever we are going for a transformer is a electromagnetic device. Definitely it has two type of losses. One we call it is a magnetic losses. The other one we call it is a copper losses. Okay, this magnetic losses will have two classifications. One I call it is a eddy current loss. The other and call it is a hysteresis loss. Okay, hysteresis loss. So if you want to reduce the hysteresis losses and eddy current losses, we going for laminating the magnetic core into the thin laminations, and it is compressed together. Okay, so in this magnetic core, we are connecting a transformer primary winding here. Okay, and I'm connecting a the secondary of the winding in the other part of the transformer. Okay. Now we are applying a voltage V1 AC voltage to the input side of the transformer. Let us say N1 is the number of turns of the primary winding and N2 is the number of turns in the secondary winding. Okay. At the moment we are applying the voltage V1 to the primary side, then a small current I1 will flow into the primary of the transformer. I call it as a I1 current. Okay. So since in this case I am not connecting any load in the secondary side, it means I am not connecting any load to the secondary side of the transformer. I can also represent this current I1 as I0. Okay. It means I0 is nothing but it is again primary current. It is a primary current under no load conditions. Okay. That is why I represent I1 as I0. So when this current is flow into the primary winding, right, then it create the magnetic flux. This magnetic flux will be circulated through the magnetic core, okay, and this magnetic flux lines, it will be linked with the secondary winding. The flux will be linked with the secondary winding. We know that according to Faraday's law of electromagnetic induction, your E is equal to minus N into d phi by dt. Okay, this is called as a self-induced EMF. Similarly, E is equal to minus m into d phi by dt, right. So this type of EMF we call it as a mutually induced EMF. Okay. So at the moment when you are applying the voltage to the primary winding, there is a small current flows from the supply to the primary winding. Then there is a EMF induced in the primary winding according to the Faraday's law of electromagnetic induction. Okay. So the EMF induced across the primary winding, I would say it is a E1. Okay. I call it as a E1. E1 is the EMF induced in the primary coil. Okay. But the flux produced by the primary coil, it is again traveling through the magnetic core. It is also linked with the secondary winding, right. So this induced EMF, I call it as a E2. This induced EMF I call it as a E2. But this E2, it is also induced because of the same flux. I call it as a phi. Okay, I call it as a phi. Actually, I told there is no load connected in the secondary of the transformer. So whatever the voltage induced here, E2, EMF induced, that voltage will be available as a terminal voltage V2. But there is no current in the secondary winding since it is not connected to the load, but the induced EMF E2 is equal to the V2. Okay. So this is what happened when you are applying the input voltage to the primary of the transformer. Okay. So we have the induced EMF in both primary coil as well as the secondary coil. Okay. And what is this I0? I0, I said it is a no load current. Normally under no load condition, that is we are not connecting any load to the secondary of the transformer, this I0 will be we will have two components, right. One I call it is a I mu, the other one I call it is a IW. Okay. This I mu we call it is a magnetizing component. I call it as a magnetizing component, and this is nothing but wattful component, right. It means I mu is a current which is responsible for circulating the magnetic flux through the magnetic core, and IW, it's a wattful component of the current I0, which delivers the energy required for the particular circuit for establishing the magnetic flux. Okay. So this I naught, that I call it is a no load current, that is equal to I mu and IW. Okay, I mu and IW. So, but this is not a algebraic sum. Actually, it is a vectorial sum, right? This is a vectorial sum. This is all about a simple transformer under no load condition. I'm not connecting any load. What happens to the transformer? Okay. Now we need to understand what is the phasor relation between the input voltage, the induced EMF in both the primary winding as well as the induced EMF in the secondary windings, right? I clearly mentioned here this is N1 and this is N2 based on your number of turns. Okay, the same transformer will act as a step up transformer, or the same transformer will be acting as a step down transformer. Okay, for example, if your number of turns N2 is greater than number of turns N2 is greater than N1, it means the voltage in the secondary is higher than the voltage in the primary. I call it as a step up transformer. And similarly, when N2 is smaller than N1, then I call it as a step down transformer. We call it a step down transformer. Okay. Now let us trying to draw the phasor diagram under no load condition for the transformer, so that we can able to understand the phasor relation between the different voltages and induced voltages, right, in a transformer. How to draw the phasor diagram for the transformer under no load conditions, right? So if you want to do that, normally I like to start from my flux line. I call it as a flux line 5. Okay, flux line 5. So we are applying the voltage V1 to the primary winding. Okay, let us consider this coil, right? It is a pure inductive coil. It means the current is going to be absolutely lagging. Okay, the current is going to be absolutely lagging. So this, when this is my flux line 5, definitely the EMF induced in the primary coil, it is lagging behind the actual flux by an angle of 90 degree. If you are assuming that it is only the inductive coil, it means the effect of resistance is going to be a very smaller one. Then I can draw a phasor, right? I call this E1. Okay, so but this E1, okay, this is EMF induced in the primary coil, but the same flux will also linked with the secondary of the transformer. Okay, the EMF induced in the secondary coil, we call it as E2. Normally this induced EMF in the secondary coil E2, it is in phasor position with respect to the E1. Okay, then I can draw, this is my E1, this is my E2 value. Okay, E1 value and E2 value. Now how to represent your no load current I naught? I said this current I naught is responsible for producing the magnetic flux in the transformer. So the current I naught can be represented like this. This is my I naught. I told I naught will have two components. One is I mu, other one I call it as IW. I mu is nothing but magnetizing component of the current. Normally it is in phase with the flux line. So I can say this is my I mu, right? And this component I call it as a IW. Okay, that's I mu is a magnetizing component of current. IW is a watt-fill component of current. Okay, I call it as IW, and this IW will supply the losses during the no load condition, right? Losses during the no load conditions. And the angle between this E naught and this E1 and I naught, that I call it as a phi naught. This angle I call it as a phi naught. Okay. So from this is very clear. This is your IW, this is your I mu, this angle is a phi naught. Then I can able to write my IW is equal to I naught into cos phi naught. Okay. By using Pythagoras theorem, we can directly get this relation. IW is equal to I naught into cos phi naught, and your magnetizing component I mu is equal to I naught into sin phi naught. Clear? So I can straight away get this relation. IW is equal to I naught cos phi naught, and I mu is equal to I naught sin phi naught, and this current I naught is the vectorial sum of I mu and IW. And this is a phasor diagram of a transformer under no load condition. Under no load condition. I hope it's clear, right? So this is my phasor diagram under no load condition. Because I am not connecting any load to the secondary of the transformer, because it is not closed, there is no current in the secondary of the transformer. We have only one current which is drawn from the primary of the supply, that I call it as a I naught. Okay. Now let us consider if a transformer, right, when it is connected to the load. Now I connect the load to the secondary of the transformer. Okay. So for analysis, I considered it is a lossless transformer. Okay. Then let us draw the phasor diagram for the transformer under a lossless condition, or we call it as a ideal transformer. We call it as a ideal transformer. But normally there is no ideal transformer in practical, right? Because all the transformer will have both the losses in due to the resistance as well as the reactance. But for as a beginner, right, let us understand what is an ideal transformer, how to draw the phasor diagram for the transformer under no load condition for the ideal transformer. It means there is no losses in both resistance and the reactance. Okay. Now I connecting the load here. Now what happens to this particular transformer? Okay. Let me understand. So if you want, I can draw it a little bit bigger. Okay. Now I consider the same transformer. This is my same old transformer, no issues. Okay. So this is my core. Now I am connecting my primary winding. This is my primary winding, no issues. And this is my secondary winding. And this voltage is I am applying the voltage V1 to the primary side of the transformer. Okay, you can take this is also primary, no issues. I'll consider this is a primary. So when you're applying the voltage V1 into the primary winding, the current I1 will move into the primary winding. I said let us assume that N1 and N2 are the number of turns of primary and secondary, right? N1 and N2. So when I1 current is getting into the primary winding, it will creating a flux phi. This flux phi will travel in this magnetic core, and it is linked with the secondary winding. Let us take this flux is phi 1. Okay. Let us take this flux is phi 1. Now I said in previous case there is no load connected to the secondary of the transformer. Now I want to connect a load to the secondary of the transformer. At the moment when you're connecting the load to the secondary of the transformer, there is a current I2. Okay, the current I2 will be circulating in the secondary winding, right? We know that whenever there is ampere turns, whenever we have ampere turns, that results in a flux. Okay, now there is a circulating current I2 in the secondary winding. This current I2 will be circulating in the secondary winding. What happens? We have the ampere turns N2 into I2. N2 is the number of turns in the secondary, and I2 is the current circulation in the secondary due to the load, right? I call it as a N2 I2. So due to this ampere turns, it producing the flux called phi 2. Okay. Normally, what is the nature of this phi 2? This phi 2 will always trying to oppose the main flux phi, because the main flux phi is the reason why we have the induced EMF in the secondary winding. So naturally it is opposing the cause. So what happens? There is another flux induced in the transformer core, due to the circulating current in the secondary of the transformer. This flux I call it as a phi 2. Okay. What happens? What is the nature of the phi 2? Phi 2, it directly opposing the phi 1. Directly will opposing the phi 1. Due to this opposition, the value of phi 1 will get decreased, because the phi 2 is directly opposing phi 1, right? So the phi 1 value is going to decrease. When phi 1 value is decreased, we know that the induced EMF in the primary coil is E1, and the induced coil in the secondary, I call it as a E2. Both these fluxes, E1 and E2, it purely depends upon the value of the flux phi. Purely depends upon the flux phi. So when the magnitude of phi 1 is decreases, what happens? The induced EMF E1 will also get reduced, because E1 is purely depends upon the phi 1. When the magnitude of phi 1 is decreases, the value of E1 will also get decreases. Let us assuming that when E1 is decreasing, right, but the terminal voltage V1 is absolutely constant, it is not changing. So there is a V1 is now it's greater than the value of E1. Okay, then what happens? There is a additional current, right? I call it as a I2 dash. Initially, I1 is a current which is flows into the primary winding. Now due to the decrease in E1, there is an additional current will move from the terminal voltage V1. Okay, so that additional current, I can say it is a I2 dash. The magnitude of I2 dash depends upon the voltage difference between the V1 and the E1. Okay, so it's clear. Now I2 dash is a new current. It is delivered by the input supply to the primary winding. Because of that, one more flux will be circulated in the magnetic flux line. Okay, so I'll represent again here. I hope it's clear for you. And this flux, I call it as a phi 2 dash. Okay, what is the nature of this phi 2 dash? Normally this phi 2 dash will be in phase opposition with respect to the phi 2. If you check the magnitude of phi 2 dash, it is almost equal to the magnitude of the phi 2, because this phi 2, right, it is results in decrease in the value of phi 1. Okay, so due to the decrease in the magnitude of phi 1, the EMF is induced and the current will increase from I1 to I2 dash. Okay, so I1 to I2 dash. Due to this I2 dash, there is another flux produced, we call it as a phi 2 dash, and this phi 2 dash and phi 2 will cancel each other. At the end of this process, we have only one flux called the phi 1. Okay, that is why whether you connect the load to the transformer or not, the flux produced by the transformer or the flux in the magnetic core is almost constant, right, when you are going for any type of transformer irrespective of the load. Okay, now we understand one thing clear here. Okay, whenever you connect the load, the input now supply an additional current called I2 dash. Okay, so this I1, normally I said it is I0, right, under no load condition, but once you connect your load, then this I0 will become I0 plus I2 dash. Now what is the current I1 which flows into the primary of the transformer? I1 is equal to I0 plus I2 dash. Okay, but this is not algebraic sum, it is a vectorial sum, right? It is a vectorial sum. I1 is equal to I0 plus I2 dash. Okay, but the value of I2 dash is purely depends upon the type of the load. Okay, so we know in general we have three type of loads in power system. The first type of load we call it a resistive load. The second one we call it is a inductive load, and third one we call it is a capacitive load, right? All the loads, it is a combination of this resistive, inductive or capacitive load, but most of the loads are belongs to RL, right? Resistive and inductive load, and the capacitive loads are very limited. Okay, so the magnitude of I2 dash, it's purely depends upon the type of a load, right? Now let us try to draw the phasor diagram for the transformer under ideal condition for different loaded conditions. Okay, now considered we are connecting a resistive load. I am connecting a resistive load to the secondary of the transformer. Okay, then what will be the nature of the current? The current I2 will be in phase with the V2, right? We know that V2 is the terminal voltage across the transformer. When it is a resistive load, the current is in phase with your voltage, is in phase with your voltage. Then how to draw the phasor diagram in for a transformer under resistive load? Okay, so if you want to draw this, I clearly told we supposed to draw a line called a flux line phi. Then the induced voltage E1, it is in quadrature with this one. I call it as E1. Okay, and E2, it is a voltage induced in the secondary winding. It is normally is it in phase opposition with your E1. Okay, it's clear. Now we have a new parameter called I2 dash. In no load phasor diagram, I have only one current. I call this current I0, but now here I have both I0 as well as I2 dash. Okay, I0 and I2 dash. So I draw this E1, E2. Okay, then how to draw this I1? This I1 is equal to I0 plus I2 dash. I know that I0 is a no load current which has two components. This is my I0. I0 will have I mu as well as the IW. Okay, I mu is the current responsible for circulating the magnetic flux, and IW is the current which is responsible for supplying the losses during the no load condition. And now after connecting the load, the current I2 will be circulating in the secondary of the transformer, and I1 is the current circulating in the primary of the transformer. If you want to draw the phasor diagram for I1, I1 is it's a vectorial sum of I0 and I2 dash. Okay, now tell me, I connect the resistive load, right? I connect the resistive load, is absolutely fine. Okay, and what is the nature of the current I2? The current I2 is in phase It's trying to be in phase with the your voltage, right? Now let's take my I2 dash, I2, right? I2 is the secondary current. It is aligned in phase with the E2, right? Then what is the I2 dash? I2 dash, it is same equal in magnitude, but it is in the opposite direction. Then definitely my I2 dash will be here. Am I right? When you know the I2 here, definitely my I2 dash, right? It is equal in magnitude, but it is just in phase opposition with I2. Okay, so I2 dash will be here. So if you want to draw what is I1, it is a vectorial sum of I0 and I2 dash. So I draw the parallelogram from I2 dash, parallel line for I0, again another parallel line for I2 dash. So this current, right, I call it as a I1. Am I right? So now it's clear. I1 is a vectorial sum of your I0 and I2 dash. I0 and I2 dash. So this is for resistive load. Okay, the phasor diagram for an ideal transformer without considering any losses, and this is for the resistive load, right? I'm connecting the resistance, right, in the secondary of the transformer. Okay, similarly, if you want to draw the same phasor diagram for the inductive load, right? We know that in inductive load the current lags behind the voltage. How to draw this? I'll draw the flux phi. Okay, same. I draw my voltage E1 somewhere here, and this is my E2. If you consider N1 and N2 are equal, then the magnitude of E1 and E2 are same, right, equal, but it is in opposite direction. Okay, now I can draw what is my I0 for simplified conditions. I'm not representing your I mu and IW. I just mentioning I0. Okay, now what is the nature of I2 dash? This is for inductive load. Definitely your current I2 dash lags behind the voltage by some angle. Okay, if you draw your I2 somewhere here, this is my I2, then where will be your I2 dash? I2 dash, it is just in phase opposition with I2 with the same magnitude. Then I can able to project my I2 dash somewhere here. This is my I2 dash. And what is your I1? It is a vectorial sum of I0 and I2 dash. I'll draw the parallelogram here. This one and this. Then I draw this. This is my I1. Okay. Now I1 again is a vectorial sum of I2 dash and what you call I0. Okay. Now actually when you look at this phasor diagram, we are not discussing about the terminal voltage, because I said it is a lossless or ideal transformer. Normally your V1 voltage axis, it is also aligned with your same E1 direction, and V2 will be aligned with your what you call the current, because I said it is for resistive load your terminal voltage, it is aligned with your current. For inductive load, definitely this current I2 is lagging behind the voltage by some angle. Okay, but I am not mentioning the voltage here. Just I draw the current for different loading conditions. This is for the what you call the inductive load. Similarly, for capacitive load, again I draw my flux axis phi. Then E1 will be here, your E2 will be here. I know that this is my current I0, that is a no load current under the. Okay, now if you are talking about capacitive load, the current will lead the voltage, right? So I'll assuming that my I2 dash, I2 is somewhere here. So I2 dash will be directly opposite to that of I2. It is same in magnitude, but it is directly in phase opposition. So when you draw the parallelogram from here, and this current I call it is a I1. Okay. Now this is a relation between your primary current, secondary current with respect to the primary induced voltages. Okay. I hope we clearly understand what is a transformer, what is the basic operating principle of a transformer, and we also discuss about how to draw the phasor diagram for a transformer under the no load condition and for the ideal condition without considering losses. We'll continue in next class. Thank you. Yeah, முடிச்சு எனக்கு காஃபி மட்டும் கொடுங்க.